Okay, we trained the model and then we have applied the trained model in the unseen data, which is nothing but the test data set. And also we have explored something like the root mean squared error and R squared, adjusted R squared, right? Those kind of things we looked at it. Now let us look at the formula for each and everything in detail, okay? These are the interview can expect this kind of questions. So which all metrics that you have used it to measure your linear regression model performance. So you have something called R squared. It is also called as a coefficient of determination, adjusted R squared, sum of squared error, and SSC. This is called your SSC. Some people they go by SSC. Some people they go by MAE, but majority of them they prefer root mean squared error. And apart from this, we have something called MAPE. So this also some people mean absolute percentage error and RMSLE. And in addition to these metrics, we will be validating the linear regression model assumption. And also we will check, are there any observations or the records which are influential. So by excluding those influential observations, we will refit the model and see if the model performance is really good. Okay, if by excluding the influential observations, if the model performance goes up, that means, right, those records are influential observations, right? So we need to exclude them. Okay, and first we will start with understanding what is R squared. R squared value, as I explained you, between ranges between 0 and 1. I'm talking about this one, this R squared, okay, 0.895. R squared, in this case, 0.895, which is closer to 1. Hence, the model performance is more or less good, right? It's a measure of how close each data point fits to the regression line. They'll ask you what exactly R squared. R squared is nothing but the proportion of a variation explained by my independent variable. Okay, that's one definition you can tell them. But in simple plain English, right? The R squared tells us how close each data point fits to the regression, how close all the data points are to the regression. You know what is regression line, right? The straight line, right? How each values are closer to this line. That is what, with the help of R squared, we can tell. And the correlation coefficient, we use a term called R. R value ranges between -1 plus 1. They'll ask you what is the difference between R and R squared. R is to find out the strength or the direction of the relation between two variables. It's nothing but the correlation. Whereas R squared tells us how close the data or data points are fits to the regression line. Okay, you can. So that is the difference between these two.
Yeah.
Okay, the R squared measures the proportion of dependent variable that has been explained by the independent variable. So supposing, let's say my R squared value is 92. Okay, 92, which means 92% of the variation of the dependent variable explained by my predictor variables. So in other words, the remaining 8% is unexplained variation. This is explained variation. This is unexplained variation. Unexplained variation. 8% is unexplained variation. Remaining 8, this is the one. That is what it tells us. Okay. So now let us look at the formula for the R squared. So we can write it this way also. R squared is equal to 1 minus SSE and actual minus the mean value of a dependent variable whole squared. Or we can say this is 1 minus SSE divided by total sum of squares. You know, this is used for simple linear regression. Now let us look at this visually. If I look at it visually, look here. So this is my x-axis value. This is my y-axis value. And I already discussed, right? I explained you this one. The mean value of your x, the average will be there somewhere in the middle in the x-axis for the x, right? The average value of your y lies somewhere in the middle of this axis, right? This is my y bar. Y bar is nothing but the average value of y. Average, this is my average value of x. The average value of x and average value of y, where it intersects? It intersects here. This is where the best fit line emanates. So the best fit line goes this, this intersected value only. Okay, and now if you see this one, this is what my predicted value. Y hat is predicted value, and this is my y value. The mean value is here. The actual value is here. Okay, you just think that way. This is my mean value of y. The actual value of x is here, and the mean value of x is here. Okay, the difference between the predicted minus mean, the difference between these two. Okay, this is a sum of squared regression. This is called as sum SSR. Okay, so the predicted minus mean, and then the actual minus mean. Actual minus mean. Okay, these two things, actual and minus mean. Right, the proportion of these two things. Predicted. That's what I mentioned it. So this is my the y predicted, y hat. So y hat minus mean whole square divided by y minus y bar whole square. So this is nothing but, see, this is nothing but predicted minus mean value is nothing but sum of squared regression. This is the explained variation. This is my explained variation. So SSR divided by y minus mean, the total sum of square. Okay, the total sum of squared total or total deviation. The SST is there in the denominator. Instead of saying this way, this is nothing but SSR explained variation divided by total variation, total variation. That is what your R squared. Okay, here I mentioned it like the sum of squared error. Okay, this is my explained variation. This is unexplained variation, right? The total variation is nothing but the addition of these two things. Explained variation plus unexplained variation is the total variation. Out of the total variation, what is the explained variation? That is what? My R squared. So we can write it like this way also. Sum of squared 1 minus, this is what is the y minus y bar, right? So that is total, this is TSS, right? 1 minus, so we can, so TSS, if you expand this one, TSS minus sum of squared error divided by TSS. What is this? Total sum of squared minus SSE, sum of squared error, unexplained variation, right? So you will get SSR divided by TSSS. That is what, see, the total deviation minus this one, right? So the 1 minus this one divided by total, no, nothing but SSR divided by TSSS, right? That is what your R square. Next one is the adjusted R square. The drawback with or the limitation with R squared is it increases the value of R squared as you keep include the independent variables to the model. Like I said, along with size plus UDS variable, if you blindly include MISC and park variables, though those two variables are not correlating with my target variable housing price, but my R squared will still increase. It misleads you by thinking that by including the other two variables also boosts my model performance. Actually, that is wrong. Okay. So simply if you include any, so like I said, I gave you the example, right? If I give you some heads, right? So some brainless heads in my team. You say 5 people are there, 5 people are performing good, and you give some brainless 5 guys. Though just because if you say 10 people I give, that doesn't mean I can improve my productivity, right? Remaining 5 people are brainless. They don't know anything. Okay. So in that case, they are non-performers, right? So in that case, if but overall, R squared will tell you, oh, you have 10 people, you have included more number of features. As you increase more number of features, the productivity will be high. R squared will be very high. That is actually conveying the wrong message. Whereas adjusted R squared, it overcomes this issue by adding a penalty. If you try to include the independent variables that are completely irrelevant. The adjusted R squared is derived from R. Okay, you need to remember this one. Look, this is the formula for this, and 1 minus R squared into n minus 1 divided by n minus p minus 1. So what is the n? N is the total number of records in your data set, and p is the total number of parameters, which is nothing but total number of columns or independent variables in your model. See here what happened, the adjusted R squared, it is adding a penalty if you keep add irrelevant variables, independent variables to your model. How? Because in the denominator, if you see, they've included p also. P is nothing, number of columns, number of features. N minus p minus 1. See, if the value of your denominator increases, what will happen? Your adjusted R squared value also will reduce, right? Simple math here. See, if you put in the denominator 200 and numerator, right? So what you will get? 1 divided by 4, right? So 1 divided by 4. And instead, if you put 25 divided by 200, what will happen? 1 divided by 8, right? So here, the value will get reduced. When the denominator value increases, the denominator. So this is how they are, penalizing the features that are not significant. See, the mathematics intuition behind this one is the denominator increases as we increase the number of features, right? Nothing but the p, the adjusted R square decreases. Okay, that is what this is the idea behind this. So the idea, so now in the interview they'll ask you, so what is why adjusted R squared, how it penalizes in the denominator as the p increases, right? The adjusted R squared will tend to decrease, reflecting the reduced power in the model. Okay. So next one is the mean absolute error. So there is something else called mean absolute error. The actual minus predicted value. You put something like the box kind of thing. This is when you take the absolute here. So right, the actual minus predicted is, even if it get negative value, it will convert as a positive value. School time we studied absolute. Absolute function, right? It will return no matter whether it's a negative or positive. It will return only the positive value. Mean absolute. This is another measure. We can say this is the main absolute error for my model 1. This is the mean absolute error for model 2. End of the day, we are going to compare which model's mean error and also mean squared error also. You can consider it. This is another measure. So mean, since we are using mean, you need to divide it by total number of observations. Sum of squared error, very well. Actual minus predicted whole squared is a sum of squared error divided by total number of observations will give a mean squared error. And now what they do is you take the square root of mean squared error. The advantage of root mean squared error. So yeah, you can here also, right? It is a measure of the average average deviation of the estimates from the observed values. The another advantage of root mean squared error is this give you the root mean squared error in terms of the target variables unit of measure, the price. Okay, it gives you the error in terms of the price, housing price in this example. Okay, so lower value of mean squared error RMSE indicate better fit. Lesser the error, better the fit. See, as I told you, if your R squared value is 90, and that means the remaining 10% are unexplained variation, which is nothing but error. And if you say your R squared value is 92, the remaining thing is the 2. That means only 2% error is the remaining 90%. Those independent variables in your model were very well helpful in terms of explaining the variation at the maximum. That means the prediction accuracy is very good. Higher the prediction accuracy. If somebody says my model has higher accuracy, that means lesser error. Higher accuracy na enna artham? Lesser error, right? In plain English. The same thing applicable here. Okay. So lesser the error, higher the accuracy. That's all, guys. Okay. So now you understood. In general, we use root mean square error to measure the model performance. Like I said, I am going to fit two models, model 1 and model 2. In model 1, I have used housing price as a dependent variable and size plus UDS, only these two variable, independent variable, I used it. In model 2, I used price as a dependent variable Here I'm going to use size plus UDS plus park plus MISC, right? MISC. So here, if I check the root mean squared error for these two models, the root mean squared error is listen to 0.82, and whereas here the root mean square is 1.82. So of these two models, which model's error is less? This one is the best model. This is how we choose the best model. 0.82 is the best model because the error is more in this model. More the error, lesser the accuracy. Lesser the error, higher the accuracy. But hence model one is the best fit. So we are going to fit two different models, and then we are going to check the root mean squared error. Okay, by taking this one, actual minus predicted value whole squared, and if you take the square root of that one, you get 0.82. For example, you get 0.1.82. So now the question is, okay, sir, in this case, I have used a linear regression model for both the models. But in this case, I have used only two independent variables. Here I used four independent variables. I knew very well these two variables are not at all statistically significant, which means these two variables are not helpful in terms of predicting my outcome variable because these two are not linearly correlated with this variable. Fine. So, is there any way can I use, even for this, can I use some other machine learning model? Yes, we have something called gradient boosted uh, tree. Okay. You can use random forest. You can use different machine learning, supervised machine learning model and try, you call that as a model 3. Model 3, same thing. Okay. Price plus size, but you are, in this case, you're using, let's, gradient boosted tree. Okay. Or gradient boosted regressor. With that, if your root mean squared error is something like 0.79, something like that, that means compared to linear regression model, gradient boosted decision tree is accuracy is good. Okay. Or the error is less. That means the accuracy is more. You need to compare the value. 0.82 is bigger than this one. Obviously, this one is lesser than this one. Hence, this model is good. So in one single session, I explained you how to compare with other models. Same thing. In case of regression problem, you have gradient boosted regression tree, and then you have something called this one, the random forest, and you can use KNN also. Likewise, there are some algorithms. It does predict. It predicts both the classification as well as the regression problem. Those algorithms you can compare it, we can fit it and then see it. Okay. Now you might be asking to check the accuracy of the model. Do I need to try so many things? Yes, you need to try with so many things. Even this one itself, what we do is we use something called the bias and variance. We have something called bias and variance. Okay. And what we are doing is, in this case, we do some kind of cross validation. Okay, so so I just explain you this one a little later. Let me just save this.